Okay, students, Assalamu alaikum. In the last lecture, we started studying about the application of energy principle within fluid mechanics, and we developed the basic energy equations, which was basically derived using the Reynolds transport theorem. The basic energy equation was this one, which is right now there in front of your screen. So you have at any point, the idea is that the overall energy in the fluid system remains same at all points in this within the fluid system. So at any point, let's say point one, so the piezometric pressure head plus the dynamic or kinetic pressure head, plus if there is any additional pump head added into the system would be equals to the piezometric pressure head and the dynamic head plus any turbine head if it is there in the system, plus the head losses. So this is basically the energy equation which we developed in our last class, and we also solved a problem related to it. And now we're going to continue forward from here. Okay, now let's discuss about the power equations. As I told you, in case of the fluid flow systems, we have the pressure heads. Those pressure heads are in the units of meters, and we can convert them into the power. So the conversion of pressure heads into power will be, for the case of the pump power, again, it will be gamma Q HP, which will be equals to m dot GHP. And I already explained to you in the last class that how gamma Q is equals to m dot G. Okay, so so this is the basic formula. So if you know the pump head HP, then either whether you know m dot mass flow rate or you know Q, which is the volume flow rate, you can use it into the formula and you can find out what is the pump power supplied. In the same way, for the case of the turbine power, it will be the turbine head. So if you know the turbine head and you know the volume flow rate, or if you know the turbine head and you know the mass flow rate, so you can use that to find out what is the turbine, what is the power supplied to the turbine. So the general form of the equation is that you can find power if you know heads. At the same time, if you know volume flow rate, then you have to use this formula, and if you know mass flow rate, then you need to use this formula. So these are the basic power equations. So let's have a problem related to it. Okay, we have a pipe which is 50 centimeter in diameter, carries water at a rate of about 0.5 meter cube per second. A pump in the pipe is used to move the water from an elevation of 30 meter to 40 meter. The pressure at section 1 is about 70 kilopascal gauge, and the pressure at section 2 is 350 kilopascal gauge. What power in kilowatts and in horsepower must be supplied to the flow by the pump? Okay, assume that HL, which is the loss head loss, is equals to 3 meter of water, and alpha 1 and alpha 2 equals to 1. So this is a base problem, a simple problem, that you have a situation like this, that we have a fluid flowing through the pipe. Okay, now the fluid has to rise an elevation. Fluid has to rise an elevation from 30 meter to 40 meters. So 10 meter fluid has to rise, and it is being flowing through the pipe. Okay, so fluid cannot move up until and unless you have a pump here, which will raise the pressure of the fluid so that the fluid can move up. Okay, so here at the before or at the entry of the pump, the pressure is about 70 kilopascal, and at the top elevation, the pressure will be about 350 kilopascal gauge. So we have the inlet and outlet pressures, and we have the inlet and outlet elevation heads. Okay, as it is mentioned that alpha 2 is equals to 1 and alpha 1 equals to 1. This is just to show that the velocity is uniform across the pipe. So since this is a pipe flow, so there might be velocity variation across the pipe. So we are just assuming that the velocity variation is not there. It is uniform across the pipe. The pipe diameter is given 0.5 meter. Head loss in the pipe is 3 meter. Okay, head loss is because of the viscous effects. So since the head loss is provided, so it's very clear that the viscous effects cannot be neglected. And whenever you have a flow through a pipe or a conduit or anything with a closed with a closed enclosure, then there has to be viscous effects in it. Okay, yeah, if the flow is within the tank, then in that case the overall the relative velocity within the tank is quite different than the velocities within the pipe, so we can ignore the viscous effects there. Okay, the volume flow rate is provided 0.5 meter cube per second. Okay, so what is asked is what power in kilowatts is required, or in horsepower must be supplied to the flow by the pump. So one thing is very clear, that the pump will be adding power to the fluid. Okay, so we need to find out at how much power is being added by the pump. How much power is being added by the pump in the fluid, so that the fluid can rise from 30-meter height to the 40-meter height. Now, while at the same time, the pressure of the fluid also rise from 70 kilopascal to 350 kilopascal. This is the question. We need to find out how much pump power required for this flow to be possible. Now, whatever the things that you have studied so far involves Bernoulli's equations, Euler's equations, and then you have the momentum equation, then you have the energy equation. Now, the thing is that point to note is that what formula are you going to use? Which equation is needed here? First of all, if you are required to find out the forces involved, if you are required to find out how much is the force in the system, then you need to use the momentum equation. But here in the question, nothing is mentioned about the force. It is not asked that how much is the force required to hold the pipe in place. It's not required. It's not asked like that. Okay, so since the forces are not required in this equation, so in this question, so we are not going to use the momentum equation. Okay, what else are we left up with? We are left up with continuity equation. We are left up with energy equation. Yes, we are required to find out the pump power required. So pump power required, we have an energy equation. Using the energy equation, we can find out how much is the pump head. Corresponding to the pump head, we can find out how much is the pump power. So energy equation is the most relevant one, which could be applied here. We could not use Bernoulli's equation because pump head is not there within the Bernoulli's equation. Also, there are head loss in the pipe, so we cannot use Bernoulli's equation because head losses are not accounted for in the Bernoulli's equation. So this is how you're going to figure out that which equation you're going to be using in which kind of problem. Okay. So before moving towards the problem solution, first of all, do you understand the problem statement, the diagram, and what is required in this problem? Okay. Now let's move over to the solution. So what we need to do is we need to write the energy equation. General form of the energy equation is this. Okay. So at point number 1, we can say that this is a point at which we have the pressure P1. Okay, and we know what is the elevation Z1, and point number 2 will be the point where we know the pressure P2 and elevation is Z2. Okay, so we can apply the energy equation between point 1 and point 2. So it will be P1 upon gamma plus alpha 1 V1 square upon 2G plus Z1 plus HP. This will be equals to P2 upon gamma plus alpha 2 V2 square upon 2G plus Z2 plus HT plus HL. I told you that this formula will be provided to you in the exam. Okay. So now what we can do is that, first of all, whatever was given in the question, we can start substituting that into this formula. So it was mentioned that alpha 1 and alpha 2 is equals to 1. So we know that what is alpha 1? Alpha 1 is 1. And we know that alpha 2 is also 1. Okay, what else? We know what is the pressure P1 gauge, and we know what is the pressure P2 gauge. Okay, so P1 is known, P2 is known. Then at state point 1, we know what is the elevation, Z1, and we also know what is the elevation, Z2. So correspondingly, we can put the values here, Z1 and Z2. Okay. Now, if you look into the figure, there is a pump here, but there is no turbine. Since there is no turbine, so the HT, turbine head, will be 0. Okay. Pump is there, so we need to find out what is the pump head. This is what is required. Okay. And then HL will also be there. And I think HL value is also provided in the question. Yes, assume HL as 3 meter. So we know the value of HL. So this is also known. So in this equation, what's left? We don't know what is V1. We don't know what is V2. But we know one thing, that there is conservation of mass, continuity. So whatever the mass flow rate is flowing, that's the same mass flow rate which is flowing throughout the pipe. Okay, so conservation of mass says that mass flow rate is constant, means mass flow rate 1 is equals to mass flow rate at 2. But we also know that the formula for mass flow rate is density into volume flow rate. Okay. Sorry. Yeah, density into volume flow rate, which is equals to density into volume flow rate. So this will be 1, this will be 2. Densities will be the same at 1 and 2 because it's the same fluid flowing. Okay, so density can cancel out. So we have volume flow rate 1 will be the same as volume flow rate 2. No. Yes, it can get affected, but here there is no rising temperature in the system. No, that's a pressure rising, not the temperature. Okay. So we have the volume flow rate. Okay, volume flow rate in the system is mentioned. Volume flow rate is 0.5 meter cube per second. Okay. So we know what is Q1. So if we know what is Q1, then that will be the same as Q2 because there is no variation in density as the flow is considered incompressible. Okay. So we'll have the formula for volume flow rate is A1 V1 will be equals to A2 V2. Okay. Now here area. Area is a cross-sectional area. At 1, the diameter is 0.5. At 2, the diameter is 0.5. So that means there is no change in the cross-sectional area throughout. So that means area 1 will be the same as area 2. If area 1 is the same as area 2, that means V1 should also be the same as V2. So we get this thing from continuity equation that V1 is equals to V2. This is that we get from continuity equation. Now we already know that what is Q. So Q is equals to AV. Okay. And if you know what is Q and you know what is the area, because you know the diameter, so you can find out how much is the velocity. And this will be the velocity same as V1, which will be the same as V2. So correspondingly, we know what is V1 square, we know what is V2 square. So now in this equation, everything is known except for HP. So we can find out what is HP. Let's see the solution here. So V1 is equals to V2. HT is 0. Substituting all the values, we know P1, we know P2, we know Z1, we know Z2, we know HL. So we can find what is HP. Okay, here one thing. Since we know that V1 and V2 are same, so even we don't need to calculate V1 and V2 because they are same. So this term will be So this term will be cancelled by this term. Okay. So here they have not calculated even that what is V1 and what is V2. Because they find out that it is same, so that means we can actually ignore them because they will cancel each other. Okay, so the end result comes out to be that pump head is 41.5 meter. And if you know what is the pump head, then you can use the power equation to find out how much is the pump power. Since we know the volume flow rate, so we can use the volume flow rate. In this case here, formula for that is gamma Q HP. So gamma is known, Q is provided in the question, HP already calculated, so the power comes out to be 204 kilowatt. Or if we know the conversion factor between kilowatt and horsepower, we can find out how much is the horsepower required. So this is the solution to this problem. If there is anything within the solution of this problem which is not clear to anybody, please feel free to ask. Is it clear? Okay, now let's discuss about the mechanical efficiency, or the efficiency in general, is defined as the ratio of power output to the power input. Okay. So efficiency is power output from machine to the power input to a machine or system. So it's P output divided by P input. Both pumps and turbines lose energy due to factors such as mechanical friction and viscous dissipation and leakage. These losses are accounted for by the mechanical efficiencies. Okay, now here is one conceptual thing that needs to be understood. When we are talking about power, there are two types of power. One is the mechanical power, which is also related to the electrical power, because you have something rotating, that's mechanical power, connected to a generator, it's going to produce electricity. The electrical power, mechanical power, they are considered to be the same. Yeah, there is a mechanical efficiency of the electrical efficiency of that generator also. The other thing is the fluid power. So fluid is moving, so it has power. Okay. When we talk about efficiency, it's always power output by power input. Always power output by power input. But depends that which one is the fluid power and which one is the mechanical power. This is the thing that needs to be understood. Okay. So let's talk about pump. So in case of the pump, if suppose you have a pump at home, okay, the pump is not going to work until and unless you connect it to electricity. So what is the input that you are providing to the pump? It is basically the electrical power, which will be eventually converted into the mechanical power. So that's the power input. But once the pump is going to start work, okay, so what it's going to do, it's going to increase the fluid power. So that electrical power which you provided as an input will be transferred to the fluid as fluid power. So fluid power will be the output. So in case of the pump, a mechanical efficiency will be the P output over P input, where P output would be the fluid power and P input will be the electrical or mechanical power. So there's a difference. So when we have the formula of conversion of pump head or turbine head into power, so that's basically the fluid power. When we use these formulas here, the power equations for the pump power, this is also the fluid power. The turbine power, this is also the fluid power. Okay, so since these are the fluid powers, so when we are talking about mechanical efficiency of the pump, so it will be P output over P input, but the P input is electrical. Okay, so here we are not going to write as m dot g HP or gamma q HP. Okay, so this is electrical power, this is not the fluid power. However, P rated here or P output is basically the fluid power. So here we can write here as m dot g HP or gamma q HP. So P output is the fluid power in case of the pump. This is a point to understand. Let's talk about turbine. In case of turbine, it's opposite. As I told you before, turbine is basically opposite to the pump. Pump, you supply electrical energy to raise the fluid power. In case of turbine, we have a fluid power available, and then we connect it to a turbine. So the fluid power is going to run the turbine, and that turbine will be connected to the generator, which will produce electricity. Okay. So in case of the turbine, the power input is the fluid power, not the power output. In case of the turbine, the power input is the fluid power. In case of the pump, power output is the fluid power. Okay. So in case of the turbine, power input is basically the fluid power, and power output is the electrical power or the mechanical power generated because of that. Okay. So when we are talking about the efficiency of the turbine, so it's again P output over P input, but in this case, at place of P input, we will have m dot G HT or gamma Q HT. And at the case of output, we cannot write it here as m dot G H. Why? Because this is not the fluid power. Okay. So these are the two devices and their mechanical efficiencies, but in the formula, there is a conceptual difference. Both are power output over power input. But in case of the pump, fluid power is the power output, not the power input. In case of the turbine, fluid power is the power input, not the power output. Okay. So you see here, in case of the pump, the fluid power is mentioned here in the numerator. And in case of the turbine, the fluid power is mentioned here in the denominator. So if you do it otherwise, it will be a mistake. This is a basic conceptual question, and I would ask you to just keep a note of it, because somehow, if required, I can ask this conceptual question in the exam. Okay. Let's talk about the overall mechanical efficiency. When we're talking about overall mechanical or electrical efficiency, so in case of the pump, we have the energy we are getting from the electric grid. Then we connect it to the motor. The motor runs the pump, and the pump produces the fluid power. Okay. So, but at each stage there is loss of energy. Okay. So the efficiency is going to be there at each stage. So the efficiency of the electric motor will be how much output divided by how much input. Okay. The efficiency of the pump will be how much output divided by how much input. And if you want to know that what is the overall efficiency or combined efficiency of the pump, so it will be the overall output divided by the overall input. Okay. So this is what's mentioned here. Similarly, in case of the turbine, we are moving the other way around. We have a fluid which is having a lot of fluid power. That fluid power runs the turbine runs the generator, and the generator produces the electricity. Okay. So when we are talking about the efficiency of the turbine, so it's again output of the turbine divided by the input. Okay. When we're talking about the efficiency of the generator, so output of the generator divided by the input. And if you want to look at the overall output of the turbine, okay, so that will be the overall output. Overall efficiency will be the overall output divided by the overall input. Okay, now let's see this problem. At a maximum rate of power generation, a small hydroelectric power plant takes a discharge of 14.1 meter cube per second. So this is a discharge. Is it a mass discharge, mass flow rate, or volume flow rate? This is volume flow rate because it is mentioned as meter cube per second. So I will write here as Q. Takes a discharge of 14.1 meter cube per second through an elevation drop of 61 meter. So that's elevation drop, delta Z. The head loss through the intakes, penstock, and outlet works is 1.5 meters. So that's the head loss, HL. The combined efficiency of the turbine and electrical generator is 87%. What is the rate of power generation? So we need to find out how much is the power generated. Okay, so it's W dot turbine. Power generation by the turbine. This is what we need to find out. Okay, so we have a situation like this, that at the top of the hill, we had water reservoir elevation 61 meter. And then this water is running down the hill. At the down the hill, we have the powerhouse where the turbine is there, and it uses the fluid power to produce electrical energy, and the elevation of down the hill is also mentioned here. Okay, so now what we can do is that we can apply the energy equation, okay, to solve the problem related to this question. And why do we know, how do we know that we have to apply the energy equation? Because we first of all, here the head losses are mentioned. So head losses are there only in the energy equation. And also we are required to find out the rate of power generation, and power generation can only be determined using the energy equation. Okay. Before moving towards the solution of the problem, first of all, do you understand the problem statement in the figure? Okay, now let's move over to the solution of the problem. Okay, we are defining here 2 points in the flow. One point is this at the top of this water level, 1. The other point is this at the bottom of the water level, 2. Okay, so these are the 2 points. Between them, we are going to apply the energy equation. So one thing is very clear, that at the top it is open to atmosphere. At the bottom also it is open to atmosphere. Here this is a reservoir. Here this is also the reservoir. And you remember we discussed this before, that whenever it is a reservoir, so the velocity of the change in the level of reservoir is almost negligible. Okay, so the velocity at 1 here will also be approximately equals to 0. The velocity at 2 here will also be approximately equals to 0. Because we are taking the points as such, both are the top of the reservoirs. One at the top hill, other at the bottom. Okay. So now let's apply the energy equation here. So if we apply the energy equation, first of all, at point 1 and at point 2, the gauge pressures are 0. So P1 is 0, P2 is 0. Also the velocities here is 0. V1 is 0, V2 is 0. We don't have any pump in between. So pump head is also 0. We know the elevation at 1, we know the elevation at 2. Okay. And the head loss is given 1.5 meter. So head loss is given. So what's left is just the turbine head. Okay, so we're going to use this. We know the elevations, Z1, Z2, we know head loss. We're going to use this to find out how much is the turbine head. So turbine head comes out to be 59.5. If you know the turbine head, you can find out how much is the turbine fluid power. Okay, so the formula for finding out the turbine fluid power will be the gamma QHT. Substituting the values, because we know the volume flow rate, and if we know the turbine head, we can find out that it is about 8.23 megawatt. But in case of the turbine, as I mentioned to you, it's the power input. Fluid power is not the case. For the case of the turbine, it's not the power output, it's the power input. But we need to find out how much is electrical energy generated. So if you want to find out how much is electrical energy generated, then we have to use the efficiency. Okay, so the efficiency of the turbine was given in the question as 87%. Okay, so whatever the power input to the turbine, if we multiply it by the efficiency, we're going to get what is the power output. Okay. So the power output of the turbine comes out to be 7.16 megawatt. Is this thing clear? Is there anything within the solution of this problem which is not clear? Please feel free to ask. So the basic difference between the Bernoulli's and energy equation is that Bernoulli equation expresses the relationship between velocity and piezometric pressure along a streamline in a steady incompressible and inviscid flow. The energy equation was developed for viscous. That's the major difference. Here it was inviscid. Here we have viscous. That's the major difference. Okay. Incompressible is the same as here. Incompressible flow in a pipe with additional energy, whether it is added through a turbine, whether it is added through a pump or extracted through a turbine, that was also not there in case of the Bernoulli's equation. So this part is also new, with additional energy being added through a pump or extracted through a turbine. This part is also not there in the Bernoulli's equation. So H, P, H, T, both were not there. Okay, in the Bernoulli's equation. And because the Bernoulli's equation was inviscid, and here we have the viscous effects, so HL is also here. So in the energy equation, we have these modifications. But suppose if we have a case where the flow is already inviscid, the viscous effects are not there, and where there is no pump or no turbine, so in the end, we are going to come up equal to the Bernoulli's equation. Even if we apply the energy equation, it will come out to be equal to the Bernoulli's equation. Okay. The other thing is that, yes, there is another difference. We are assuming uniform flow velocity at the inlet and exit ports in case of the Bernoulli's equation. But in case of the energy equation, we are now using alpha 1 and alpha 2 in the main formula. Okay. So this alpha 1 and alpha 2 is basically taking into account the non-uniformity within the velocity profile, okay, inside the kinetic effect. So obviously the non-uniformity in the velocity profile is going to affect the kinetic potential or the kinetic energy. Okay, so we have this alpha only associated with V1 square upon 2G and alpha only associated with V2 square upon 2G. So this is again a very, very important question from the conceptual questions point of view. What is the difference between Bernoulli's equation and energy equation? There are three differences mentioned. Okay. One difference is viscous effects. The other difference is the additional energy by pump or by turbine, either extracted or provided or added. And the third difference is the non-uniformity or within the velocity profile. Okay, we are assuming that it is uniform velocity profile in case of the Bernoulli's equation. But in case of the energy equation, now we are taking into account that yes, the velocity profile might not be uniform, it might be non-uniform. And then we are taking alpha 1 and alpha 2 are basically to take into consideration about that. So this is a very important question. Normally, if I, for example, if I want to give a short question, conceptual question of 3 marks, so these are 3 points. Okay, transitions or abrupt expansions. Let's have a break of 10 minutes, and then we will start this topic. Okay, so let's start with the next topic, which is about abrupt expansion. So basically, transitions. So now we have studied energy equation, momentum equation, and continuity equation, and they can be used together to solve a variety of problems. The use of 3 equations in combination is illustrated to obtain the head loss in flow through an abrupt expansion. Now, what is an abrupt expansion? Suppose I have a small pipe and then I have a big pipe and I connect the 2 pipes together. Okay, so we'll have an abrupt expansion, sudden expansion. On the other hand, suppose if we have a situation like venturimeter, In case of venturimeter, you have a constriction and then you have expansion. Okay, so this is gradual expansion, and if it is sudden expansion, then this is sudden expansion. So gradual expansion would be something like this. Sudden expansion is like this. So gradual, this is gradual expansion. This is sudden expansion. Okay. So suppose if we have here a confined jet of fluid from a smaller diameter pipe discharges into a larger pipe and creates a zone of separated flow. So the jet streams are initially straight and parallel, and the piezometric pressure distribution across a jet at section will be uniform. Okay, for analysis, apply the energy equation. If we apply the energy equation, since this is an abrupt expansion case, there is no pump, there is no turbine. So HP and HT will not be there. We're going to end up with this equation. If we apply the momentum equation, so for the case of momentum equation, this is our control volume. Okay. Now within this control volume, this is the, you can say this is the entrance of the control volume. So you're going to have a pressure at this end. You'll have a force due to pressure at this end. Okay. Then we'll have the component of forces will be the weight acting in the downward direction. So these will be the three forces that we have due to pressure P1, due to pressure P2, and due to the weight of the fluid. Okay, and we won't have any momentum accumulation term because considering that the flow is steady and the dimensions of our control volume are not changing, so the momentum accumulation term will be zero. Then we are going to have momentum inflow and momentum outflow. So you'll have momentum single inflow and single outflow. So this is this momentum outflow, rho V2 square A2, and this is the momentum inflow. And inflows are always negative. This is something that you have already studied in the momentum chapter. So this will be our momentum equation. If we divide this equation by A2, if we divide this equation by gamma A2, divide the whole equation by gamma A2, okay, we are going to come up with this thing. Okay, this is another equation. So that was the energy equation. You can say equation 1 is the energy equation. Equation 2 is the momentum equation. Then the next one is the continuity equation. Okay. So continuity equation V1 A1 will be equals to A2 V2. This will be the continuity equation. Now what we can do is that we can combine all the three equations together. If we combine all the three equations together, so from the continuity equation, what we have is that A1 by A2 is equals to V2 by V1. Okay, so here we have in the momentum equation A1 by A2 just substituted by V2 by V1. Okay, and here we have P1 upon gamma minus P2 upon gamma. Here we also have P1 upon gamma, and if we take P2 on the other side, we'll have minus P2 upon gamma. So if we subtract equation 2 from 1 or 1 from 2, so pressure terms will also be cancelled. So what we are going to left up with is an expression for HL. Pressures will be cancelled, and the expression left for HL will be V1 minus V2 whole square upon 2G. Combining the three equations together, continuity, momentum, and energy equation, we can get an expression for HL like this. Okay, you can try this on your own. How do we get this expression? Now, in this case, since if a pipe discharges into a reservoir, Suppose if the larger pipe is a very big pipe, like a reservoir, like a tank, okay? So in that case, the velocity in that big pipe will be considered very, very small compared to the smaller pipe. And so very, very small compared to the smaller pipe, their squares will be negligible, okay? So V2 could be considered as negligible. If the pipe is discharging into the reservoir, we can presume that V2 is approximately equals to 0. Okay. So we're going to end up with HL equals to V1 square upon 2G. So that will be the head loss while the fluid is entering into the reservoir. So this is the velocity head in the pipe. This energy is dissipated by the viscous action of the fluid in the reservoir. So this was for the specific case of abrupt expansion. Now let's see a problem associated with it. Okay, a pipe 30 centimeters in diameter carries water at a rate of 0.707 meter cube per second. So this is volume flow rate. It's 30 centimeters is a diameter. The pipe contracts to a diameter of 20 centimeters. So this is, you can say, diameter 1. This is the bigger diameter. And this is, you can say, the smaller diameter. Smaller diameter, either I can write here small d, or I can write here as d2. The head loss through the contraction is given by this. This is the head loss given by the contraction, HL, where V2 is the velocity in the 20 centimeter pipe. What horizontal force is required to hold the transition in place? What horizontal force is required? What horizontal force is required? So they're asking force. Since force is being asked, that means you have to solve the momentum equation. Force is there only in the momentum equation. It's not there in the energy equation. It's not there in the continuity equation. Okay. So we are asked what is the F, or you can say Fx, horizontal force required to hold the transition in place. Assume alpha 1 and alpha 2 equals to 1. Okay. So this is the diagram for the equation, where we have a bigger pipe, bigger diameter pipe, and it's going into the smaller diameter pipe. It's connected with a smaller diameter pipe. Bigger diameter pipe is 30 centimeter. Smaller diameter pipe is 20 centimeter. The pressure in the pipe is mentioned. Yes, 10 degrees centigrade, 250 kilopascal. This is the pressure in the bigger pipe, P1. This is mentioned. Okay, volume flow rate in the bigger pipe is 0.707 meter cube per second, as mentioned, and we need to find the force required. Okay, so force required to hold it in place. Okay. The question is that will there be any force acting, will there be any force of the fluid acting on this? Definitely, because we have a case where the pipe diameter is decreasing. So if I force the fluid through this, okay, and if I do not hold the pipe in hand, or so it will push the pipe, the fluid is going to push the pipe with it, okay, because the pipe was being constructed. So when the fluid is going to pass through this constructed area, it's going to push the pipe along with it. Okay. So there is definitely a force of the fluid which is going to act on this construction, and so the pipe needs to be held, or counter force should be there to keep the pipe in place. So we need to find out how much should be the counter force. In that case, we need to find out how much is the force of the fluid acting on this pipe. Okay. So in order to solve the problem, what we need to do is we need to apply the momentum equation. This is the momentum equation. Now we don't need to go into the details of it since we have already covered momentum equation in many problems in chapter number 6. Okay. So here this is the equation. Summation F is equals to d by dt integral of control volume rho v dv. This is the momentum accumulation term. But normally the momentum accumulation term will be 0 because the flow is considered steady and because our control volume is fixed and the boundaries are not moving. Okay, so there is no momentum contained. So then plus we will have the momentum outflow minus we'll have the momentum inflow. So if we consider this as our control volume, so we will have a single inflow, single outflow. Okay, so summation sign will be gone. So let's talk about the summation Fx term. Okay, so we'll have P1A1. The pressure here will be P1. So that will be P1A1. Here it will, the pressure will be like this. So it will be P2A2, but in the negative direction, plus Fx, whatever the force here. Okay, so we'll have P1A1 plus Fx minus P2A2. So these are the force terms. Let's discuss about the momentum terms. So this is the summation momentum outlet minus summation momentum inlet. Since there is one outlet, one inlet, summation will be gone. So it will be m dot v2 minus m dot v1. Okay. So this will be the momentum effects. So now if we substitute the values, we're going to get P1A1 minus P2A2 plus Fx equals to m dot v2 minus m dot v1. Already mentioned that the momentum accumulation term will be 0. Okay, so here we have m dot, we know it's basically m dot is rho q. So we can substitute m dot here as rho q. Okay, so we have Fx equals to rho q v2 minus v1 plus p2a2 minus p1a1. This is what we have now. So Q is mentioned, Q is provided in the problem. Okay, so if you know Q, so formula is Q is equals to AV. So A1 V1 or A2 V2. So since Q is known and we know the diameters, so we know the areas. Okay, so since we know Q and we know the area, since we know the diameters, so we can find out what is V1 and what is V2. Okay, so V1 and V2 are known here, density is known here, Q is known here. Okay, so now we need to find out what are the pressures P2 and P1. Area is known, so P2 and P1 are unknown. If we know P2 and P1, we can find out what is the force here. Okay, P1 is known because it was mentioned in the question. P1 is 250 kilopascal, so at 250 kilopascal gauge. Okay, so P1 is known. So now there is only one term left, P2. If we know P2, we can find out what is Fx. Okay, for finding out P2, we have to now solve the energy equation. I'm not going to say Bernoulli's equation. Why? Because this is a pipe flow, and whenever you have pipe flow, there are head losses, and you cannot use the Bernoulli's equation where the viscous effects are there and head losses are there. Okay, so we have to use the energy equation. So if we apply the energy equation, so within the energy equation, first of all, it is a horizontal pipe. So Z1 and Z2 are same. So they're going to cancel each other. Okay. And then there is no pump. There is no turbine. So HT and HP will also be 0. So what we are going to left up with is P1 upon gamma plus V1 square upon 2G equals to P2 upon gamma plus V2 square upon 2G plus HL. Okay. Now V1 and V2 we know, we already calculated. Okay, P1 is given in the question, P2 we need to determine. HL is right now not known, but it was given in the question that HL is equals to 0.1 into V2 square upon 2G. Okay, so HL is a function of V2 and we already know V2, so we know what is HL. Okay, so here what we can do is just substitute the values. HL is also, because HL is a function of V2 and we know V2. So we can find out what is HL if we know what is V2. Then here we can substitute all the values because only P2 is unknown then. So we can find what will be P2. Once we know P2, we can substitute here. And we can substitute this value here to find out what is Fx. So the Fx comes out to be 8.16 kilonewton applied in the negative x direction. So you see here, this is a problem where you are using the concepts of the last 3 chapters together. We use continuity equation to find out the velocities. Continuity equation was used in chapter number 5. Then we wanted to find out the force. This is what we are using to the momentum equation, which we developed in chapter number 6. Okay, and in this chapter, we were working with the energy equation, and we cannot find out F until and unless we know what are the pressures, and in order to find out P2, we had to use the energy equation. So the concept of chapter number 5, 6, 7 all together used in this question. Okay, 5, 6, 7 all together used in this question. So normally we enjoy giving such questions in the exam where multiple concepts are judged from the students by using a single question. So I don't need to provide a separate question for chapter 5 and separate question for chapter 6 and a separate question for chapter 7. Rather, I can provide a single question where all the concepts of chapter 5, 6, and 7, or majority of the concepts of chapter 5, 6, and 7 are included in it. Okay. And this is another point, that even though this might be true, that in the final exam, I will be canceling out some of the chapters, but that does not mean that if I'm canceling out that specific chapter, the concept related to it, if used in another chapter, will not be used. Okay. So suppose if I am canceling chapter number 5 for the final exam, that does not mean that the concept which is used here in chapter number 7 from the chapter number 5 will not be used. Okay, so you might be asked from here. Okay, so anyways, that needs to be understood. Prerequisite is a prerequisite. You cannot totally ignore it. Okay, that was the solution to that problem. If there is anything within this problem which was not clear, please feel free to ask. Okay, now let's see this problem. The discharge in the siphon is 0.08 meter cube per second. D is equals to 20 centimeter, lengths L1 and L2 are 0.9 meter. Determine the head loss between the reservoir surface and the point C. Determine the pressure at point B if 3/4 of the head loss as found above occurs between the reservoir and point B. Assume L5 equals to 1.1.0 at all locations. Now the question is that what is a siphon? Siphon is something that you have used that you have studied in your secondary school probably, and also during your metric or intermediate knowledge. And this is something which is a technique used by the petrol thieves. So if somebody wants to take petrol out of your car, what he's going to do? He's going to somehow open the petrol cabin. They're going to put a pipe. They're going to suck a little petrol, put the pipe down, and the petrol is going to come out on its own. It's because of the siphon. Okay. So anyways, so here we have a siphon here. This is a container which is containing water. Okay, so a pipe is placed in it. The diameter of the pipe is provided. And obviously the pipe is filled with water and is being placed at a certain level below the water in the tank, so that now the water is going to siphon out of this water tank. So in this case here, the water flow rate is 0.08 meter cube per second, which is basically Q. diameter is 20 centimeter, L1 and L2 are 0.9. It is mentioned here, this is L1, and L2 is this. Determine the head loss between the reservoir surface and the point C. Now, reservoir surface is open to atmosphere and point C is also open to atmosphere. So that means the pressures and both the points, the gate pressures will be zero. So if we apply the energy equation between point 1 and point C, so P1 will be 0 and PC will be 0 because they both are open to atmosphere. Obviously, in this case of a siphon, there is no turbine, there is no pump here. Okay. Elevation, we can consider at point 2 will be at 0 datum. If we consider it as 0 datum, so elevation at Z will be 0. Okay, and the elevation of point 1 will be L2, which is actually 0.9. So this is known. We don't know what is the velocity V1. We don't know what is the velocity VC. Okay, velocity V1 we know because V1 is inside the container. And in case of the container, inside the container, the velocity is considered to be approximately equal to 0. It's very, very small. So V1 will be 0. So we are just left up with VC and HL. So we get an expression of HL as 0.9 minus VC squared upon 2G. Okay. Now, in this problem, since we know what is the volume flow rate and we know what is the area of the pipe, so we can find out what is AC. So correspondingly, we can find out what is VC. Now we can substitute the value of VC into the main equation. We can find out what is HL. In the second part of the question, it is asked, determine the pressure at point B. So if we want to find out the pressure at point B, we can apply it between point 1 and point B instead of applying at point 1 and point C. So in the same way, here we will have, because the velocity at VB and VC will be the same since the area is same of the pipe. Okay, so we know already what is VC, so we know what is VB. So the only thing unknown will be the PB in this equation, so we can solve it to find out how much is the PB. So this is the solution to this problem. If there anything within this solution which is not clear, you see here it was mentioned that between point, if 3/4 of the head loss occurs between reservoir and point B. So from this point to this point, the head loss was 3/4 of the overall head loss, 3/4. Okay. So overall head loss we already determined. So 3/4 of it will be this, based on if the overall head loss is this. Okay. And between between the reservoir and point B, again the height will be 0.9. Elevation difference will be 0.9. So you can say the elevation for reservoir is 0.9 and elevation for point B is 1.8. So if you just substitute all the values, you can find out what is the pressure at B. So that's the solution of this problem. If there is anything within the solution of this problem which is not clear to anybody, please feel free to ask. Okay, now we have the last topic of this chapter, which is basically hydraulic and energy grade line. We recall that we have the energy equation like this: P1 upon gamma plus V1 squared upon 2G plus Z1 plus HP equals to P2 upon gamma plus V2 squared upon 2G plus Z2 plus HT plus HL. The terms of the equation above have dimensions of length. This has led to the conventional use of the hydraulic grade line and energy grade line. Now, hydraulic grade line in a piping system is formed by the locus of points located at a distance P upon gamma above the center of the pipe, or P upon gamma plus Z above a pre-selected datum. So hydraulic grade line is basically what? It is the piezometric head. Hydraulic grade line is the piezometric head above a specific datum. So you have a specific datum or a reference point. Suppose you have this is the datum. This is the datum or the reference point. So corresponding to that datum, how the piezometric head is changing throughout the fluid flow system, that is basically the hydraulic grade line. Okay. When we talk about the energy grade line is formed by the locus of points at a distance of v square alpha v square upon 2g above the hydraulic grade line, or the distance above the datum. So if we add the kinetic head to the hydraulic grade line, that will become the energy grade line. Okay. So in case of the energy grade line, we have to add the kinetic head, which is alpha v square upon 2g, added to the piezometric head. So this was the piezometric head, which is the hydraulic grade line. Okay, so hydraulic grade line plus kinetic head is the energy grade line. Now, from the exam's point of view, what is the difference between hydraulic grade line and energy grade line? This is a question which could be asked for 2-3 points, because there are several differences between hydraulic grade line and energy grade line, which I just discussed. Can hydraulic grade line be greater than energy grade line? Can energy grade line be greater than hydraulic grade line? Explain your answer with proper justification. This is another conceptual question. Okay. Following are the helpful hints for drawing hydraulic grade line, energy grade line. The energy grade line is positioned above the hydraulic grade line by an amount alpha v square upon 2g. Thus, the hydraulic grade line and energy grade line coincide if velocity is 0. This is another question. If the velocity of the fluid becomes 0 at certain point, what will happen to the hydraulic grade line and energy grade line? Will the hydraulic grade line be higher than energy grade line, or energy grade line be higher than hydraulic grade line, or they both be at the same point, or they both coincide? Okay. The hydraulic grade line and energy grade line slope downwards in the direction of flow due to the head loss in the pipe. This is another question. Why does HGL and EGL slope downward in the direction of flow? The answer is because of the head loss in the pipe. If there was no head loss, then they will not slope down, then they will remain straight. If the pipe has uniform physical characteristics, diameter, roughness, shape, the HGL and EGL along the pipe will be straight lines. So under what condition HGL and EGL could be straight line? Okay, with the slope delta HL over delta. So if this is the condition, the diameter, roughness, and shape are uniform. A jump occurs in the HGL and the EGL whenever useful energy is added. So whenever you have a pump, there is a sudden jump in the HGL or EGL. Whenever there is a turbine, there is a sudden drop in the HGL or EGL. So why is there a sudden jump? Going up or going down? Going up will be because of the pump. That the answer will be, so it will be because of the pump, because additional energy is added into the fluid at that point where the pump is there. If it is going suddenly jumping down, then not head loss, then basically the turbine head, because turbine is extracting energy at that point, sudden. Okay. If it is head loss, it will not be sudden, it will be gradual. Okay. So this is again a question. There are several questions that can come out, several conceptual questions that can come out from the topic of hydraulic grade line and energy grade line. Such as occurs with the pump. A drop occurs if the useful energy is extracted. A drop occurs if the useful energy is extracted from the flow, as occurs with the turbine. In a pipe or a channel where the pressure is 0, the HGL is coincident with the system elevation. So if the pressure is 0, so hydrostatic pressure head will be 0. So whatever the HGL will be the same as Z, whatever the elevation of the system. If a flow passage changes diameter, the velocity therein will also change. Hence, the distance between EGL and HGL will change. Basically, if the velocity is constant, then the distance between EGL and HGL would remain same. Okay, so this distance would remain same. But suppose if the velocity is increasing or the velocity is decreasing, okay, then the distance between HGL and EGL will change. So suppose if the velocity is decreasing, then it will become closer, closer, closer. If the velocity is increasing, then it will become far away, far away, far away. Because this difference is basically just the kinetic head. The kinetic head is v squared upon 2g, and v is the velocity. So if the velocity is increasing, kinetic head is increasing. So the distance between HGL and EGL will be increasing. If the v is decreasing, then the kinetic head is decreasing. If the velocity becomes zero, the fluid becomes stationary at some point, then HGL and EGL will become zero. But EGL can never go below HGL. This is again a short question. Can EGL go below HGL? Or what could be the minimum value of EGL? How much could be the minimum difference between EGL and HGL? Zero. But it's not possible that the energy grid line can go below the hydraulic grid line. So let's see a problem associated with this. A pump draws water from a reservoir where the water surface elevation is 520 feet and forces the water through a pipe 5,000 feet long and 1 feet in diameter. This pipe then discharges the water into a reservoir with water surface elevation of 650 feet. The flow rate is 7.85 CFS. And the head loss in the pipe is given by 0.01 L by D V squared upon 2G. Determine the head supplied by the pump and the power supplied to the flow. And draw the HGL and EGL for the system. Assume the pipe is horizontal and is 510 feet in elevation. Okay. So we know the elevation of the pipe. So this is the situation. We have one reservoir. We have another reservoir. These two reservoirs are too far away from each other. So there is a pipe which is connecting the two reservoirs, and there is a pump in between which is forcing the fluid from one reservoir and making it to flow into the other reservoir. Okay. So this is the situation. The free surface of both the reservoirs, elevation for the free surface is provided. And for the case of the pipe, the elevation is also provided, the length of the pipe is provided, diameter of the pipe is provided, the flow rate through the pipe is provided. Okay. So we need to find out how much is the energy required, how much is the energy supplied by the pump. Okay. So this is asked. Determine the head supplied by the pump and the power supplied to the flow. So let's see the solution. Since we want to find out the head supplied by the pump, so we have to solve the energy equation, energy head equation. Okay. So again, we have at both ends, we have the reservoir. So for the case of the reservoir, velocities are considered zero. Okay. So V1 will be 0, V2 will be 0. Both are open to atmosphere. So P1 0, P2 0. There is no turbine in between. So HT 0. Elevation for one reservoir is known. Elevation for the other reservoir is also known. Okay. And we need to find out how much is the pump power. So that's how we're going to end up with this equation. Okay. HL. Now here in this equation, HL is unknown, but HL, the formula for HL is given. Formula for HL is 0.01 L by D. Length is given, diameter is given in the problem. Velocity is something which is not known. Okay. So in order to find out the velocity, we can use the continuity equation, which is Q is equals to AV. Okay, since we know what is Q and we know the diameter of the pipe, so we know what is area, so we can find what is the velocity. So the velocity comes out to be 10 feet per second. So now we can use the value of velocity in the formula for HL given in the question to find out what is HL. And once we know HL, we can substitute it into the main equation to find out what is the HP. So this will be the pump head. And then if we know the pump head, then we can use it into the formula of the power to find out how much is the pump power. So the pump power comes out to be 159 horsepower. If we want to draw the HGL and EGL, so basically these are the 2 points where the velocities are zero. So the HGL and EGL will be just the top of these reservoirs, 0.1 and 0.2. Okay, and then we have a velocity throughout the pipe. Okay, so we'll have a difference between HGL and EGL. So there will be a little difference between HGL and EGL, and how much will be this difference? It will be equal to V square upon 2G. However, as the fluid flows through the pipe, there is a gradual decrease in the HGL as well as in the EGL because of the head losses. Okay, and at the point of pump, there is a sudden increase. So at the pump, there is a sudden increase, but then there is a gradual decrease. So this is basically the HGL and EGL drawn for this problem. Okay, after this problem, we have another problem here, but this is again a very similar problem to what we have just done before. So I would like you to go through this one yourself. Okay, if there is anything you want to ask, you can ask me out later. And with this, our chapter number 7, which is basically for the energy principle in the fluid flow, is finished. If there is anything anybody want to ask regarding this chapter, you're free to ask. Okay, so that's it for today, and we can discuss okay, that's it for today.